I want to do today, very short, I want to look at the first homework assignment and essentially get you guys ready for that. So what we're talking about here is exclusively linearization. We're not really going to worry about differential forms of derivatives or differential approximations. We're just using linearization, right? So we're going to take a linear model of a function, which is this, right? This is our formula. So L of x, the estimated output of the function, is f of a plus f prime of a times x minus a. Now, where do we get that? Let's remind ourselves, because that's a lot to remember. Don't memorize it. Just always derive it for yourself. It's easy, right? All it is point slope form. That's it, right? It's just like if we've got a point at a f of a. Yes?
So we could technically replace the values in that equation with one set or more for the other. To help us kind of
Yeah, right. Well, what is f prime of a? That's just m, isn't it? Right.
Yeah.
Right. And L of x is just y.
And then f of a is really just y1.
Yep.
Okay.
And a is x1. Yeah. Right. That's all it is. We're just taking point slope formula. Y minus y1 equals m times x minus x1, where m is the slope and x1, y1 are just the coordinates of some known point, right? And solving for y, that's all we did. That's it, right? Only difference here is that this is going to be our m, this is our x1, this is our y1, and that's y, right? Make sense? Okay, and that's, look what we did right here. That's it, okay? And then we just solve for y. That's it. Okay, so let's try a couple here. So we want to do something like this. How about write the equation of the line that I want to do. Have you guys do three things. I skipped the graphic part. Write the equation of the line that represents the linear approximation to the following function at a. It's supposed to say at the value at the. Yeah. Yeah, give him point A. There we go. How about that? All right. Okay, give him point A. So let's do that first. So what do we do? What's our formula for linearization? I tell you, let's do this. Let's write it this way. Y equals y naught plus m times x minus x1, right? But we're going to change that. What is y?
L of x.
L of x, right? That's what we're calling our output, the function that we're using, right? Y always corresponds to f of x, or in this case, L of x, equals y naught is f of a, which for us is going to be f of 1, okay? Plus, what's m? F prime of 1, good. Times minus 1. Yeah, there it is. Okay. And we have our function here, so we should be able to plug in stuff for all that, right? If this is f of x, what's f of 1? 8. Yeah, 11 minus 3 times 1 squared, 11 minus 3 is 8. Okay, what's f prime of x? Negative 6x. So f prime of 1 is what? Negative 6. So we can plug everything in there, right? So our linearization then just becomes L of x equals 8
plus negative 6 times
plus negatives. Okay, good. And I'm going to write that as minus 6 times x minus 1, right?
Yeah.
There it is. There's our linearization.
Yay.
Okay?
So then you can solve for the one that I want you to solve for.
Exactly. Yeah, right. So now we'll use the linear approximation to estimate the given function value. So what are we trying to estimate? This, right? So f of 1.1 is approximately equal to L of 1.1. But it's easy to calculate L of 1.1 because it's linear, right? What's 1.1 minus 1? 0.1 times 6.
0.6.
0.6. So 8 minus 0.6.
7.4.
Boom. Got it.
Whoa.
Okay? Make sense?
I think so.
Okay, easy. Now, okay, so the percent error. The percent error, all you guys are going to calculate in college, you'll calculate this in science, you calculate this all the time. Percent error. So we want to calculate percent error. That's the same thing as relative error. So what is that? Well, that's going to be relative error is always approximate minus exact divided by exact. Okay. So what is approximate minus exact? Well, I mean, this is kind of a goofy thing to do in a way because we have to actually calculate what the exact value is to do this, right? So our approximate value was 7.4. To find the exact, we'd have to go back and actually evaluate f of x at 1.1. So what's that give us if we calculate the exact? F of 1.1 is 11 minus 3 times 1.1 squared. Well, what's 1.1 squared?
1.2.
There it is, 1.21 times 3, 3.63. So 11 minus 3.63, 7.37.
What
Yeah.
the? Oh my
Yeah,
gosh.
Yeah.
Oh, I was like, oh my gosh.
Okay, so then if we want to do, that was pretty impressive, huh? So then if we want to do this, if we want to compute the percent error, let's do that down here then. So all that is, first of all, the relative error would just be approximate minus exact. So that's going to be 7.4 minus 7.37 divided by the exact. Okay, so what's the exact? Well, the exact in this case is 7.37. Now notice that they have got these absolute value bars in here, which means that they're only wanting this. See, I kind of objected that a little bit. It makes sense to put the absolute value bars on the bottom, but I think it's of some use to keep the sign here, honestly, right? Because this ends up being positive. If I do this, I end up getting positive 0.03 divided by 7.37, right? If I turn that into a decimal, what does that end up being? Carson, just do this in your head again. What's that real quick?
What?
I'm kidding. Use your calculator.
Well, I.
Maybe a tough one to do.
0.004.
Say it again.
0.004.
0.004. Take it out 2 more.
0.07.
0.07. Okay. If we want to turn that into a percent, well, then we just multiply. Then we just multiply by 100, right? So as a percent, we would get percent error would equal, move the decimal 2 places, and I get 0.407%. Okay,
That's a good error.
that's pretty good, right? I mean, maybe. I guess it depends on what our needs are for this, but that seems pretty good. Okay, less than 0.5%. The sign to me is kind of important here because it's positive. What does that mean? Our approximation was too big, right? We were a little bit off. It was a positive percent error. If our approximation had been like 7.35 or something, then we would have gotten a negative relative error or percentage error, and it would have meant that we undershot a little bit. So I actually kind of think it's important to include the sign, but these guys don't, so we won't. So theirs would have been, it's always going to be positive. It's just going to give us a straight percentage error, which just tells us how far off we are. But it doesn't tell us if we overshot or undershot. Not that big a deal, honestly. You see it both ways, but I sort of like thinking back to my physics days, like we would have always kept that as a signed answer. Bottom we would have made absolute value, but the top we wouldn't have, right? Because we want to know, did we overshoot or undershoot? Okay, make sense? Let's try another one. So how about this guy? We want to write an equation of the line that represents the linear approximation. So this time, let's see if we can go a little quicker on this. See if we can jump right to the answer. So we've got f of x. Oops.
The graph.
I don't know what I did. We've got our f of x. What is f prime of x going to be? Derivative secant is?
Negative cosecant.
No.
Cosecant.
Oh, it's like is it like?
Is it secant, tangent?
That's it. Secant tangent.
These ones are fun.
Secant x.
Tangent.
Tangent x. Okay, and so what's our value? Well, our value of a is 0, which is pretty convenient, right?
Yeah.
Okay, so then we need to know what is f of a? That's just f of 0, which is what? What's the secant of 0? You guys might be, I'm not smart enough to think about secant in terms of what.
It's 1.
I always think of it in terms of its reciprocal, cosine, right? Secant is 1
1
over cosine. Exactly. And cosine of 0 is 1, so 1 over 1 is 1. Good. Okay. How about f prime of a? So f prime of 0. We already said secant is 1. How about tangent?
0.
0, yeah, because I get sine. Tangent of 0 is sine of 0 over cosine of 0, which is going to be 0 over 1. So I get 0 for that. Okay? So if I want to come up with a linearization then, well, what's that going to be? Our linearization is L of x equals what? No, first of all, f of a plus
F prime of a times x minus 1.
minus
No, x minus a.
x minus a, right. So for us then, that's going to become L of x is, f of a is 1, right? Because it's f of 0 for us, right?
Yeah.
Okay. Plus 0 times, who cares, right? X minus 0, that's 0 times whatever is 0. So our linearization, how about that? Our linearization is just 1. Yeah. Our linearization happens to be a horizontal line. Okay? And so what is our approximation of f of 0.02? That's approximated by L of 0.02, which is what? 1. L of x is 1. The output is always 1. How about that? Okay. So how do we do? Let's check our percent error. We'll do it their way this time. It'll all be positive. So percent error then would just be the absolute value of our approximate minus exact, right? So our approximate was 1 minus, well, what is, so we're going to need a calculator for this. We're not going to know this answer, but what is the secant, because that's our original function, right, is secant of x. So secant of 0.02. How do you take secant on your calculator?
That's a good question. I just asked that myself.
Find cosine and put 1
Yeah,
over.
exactly. You just find cosine and then take the reciprocal of it. Yep.
Do I have to do arc cosine or just cosine?
No, just regular cosine.
Okay.
Yeah, so cosine of 0.02, and then you hit the 1 over x button.
Sorry guys, it takes a second.
It's going to be real close to 1, isn't it?
Yeah, it is close, but I messed up, so.
I don't know.
No, I didn't reciprocal. But that's what.
If you do reciprocal, you got to put parentheses probably.
1 divided by. Oh my gosh, it's
1.0000000.
Yeah, okay, so what is it again? It's 1 point.
Zero,
1, 2,
zero,
3,
zero,
4, 5, 6, 7 zeros.
Then a what?
6, 1.
6.
6, 1?
6, 0, 9, 2, 3, 4, 8, 7.
My calculator.
So what would I write up here? After those 6 zeros, I write
6,
6.
0, 9.
Okay, that's good enough, right? So then, I mean, my goodness, that's going to be a pretty small error. So we're going to get the absolute value of 1 minus 1.000000609 divided by the absolute value of our exact value. Which is what?
My calculator gave it to me in like the exponent form.
Okay, so what's it tell you?
Negative, just ignore the negative.
Okay.
6.099999
Okay, let's call it 6.1.
e to the negative 8.
So if we multiply by 100, it's just to the negative 6, right?
Yeah.
So then that means as a percent,
It's 0, 0.
yeah, that's going to be 0.12345, 61%.
I don't know.
That was a pretty good approximation, right? Not bad. Okay. That works pretty well because think about that. We hit secant, if we think about the graph of this, we were at 0, right? Yeah, so secant of 0, here's what our secant function looks like. This is out at pi halves and negative pi halves. That's where it's going to go asymptotic, right? Because secant of pi halves wouldn't work. That'd be like 1 over cosine of pi halves. Well, cosine of pi halves is 0. So it does this. If that's 1, that's what our secant function looks like, right? So doesn't it make sense then that at 0, we've got a horizontal tangent line? How about that? Okay. Good. Okay. Okay, so how about this? This is kind of a fun little, this is a nerdy party trick you can do. Impress your friends, college. Okay, so could you estimate, just by using your intellectual powers, could you get a pretty good estimate of, let's see, okay, actually, no, this isn't the party trick. That's coming next. This is what we got to do first, though, to prep for it. So if I'm telling you that f of 5 is equal to 3, we know that, and f prime of 5 is equal to 6. Could we estimate what f of 4.9 is?
Yes.
Well, I guess we can. Okay, forget what you saw there. Okay. So how could we do that?
Let's see.
Use our linearization.
So f of 4.9 is approximated by our linearization, which is what? What's the value of a that we got to pick a value of a. The reason that presumably we would need to do this is because 4.9 is probably not a convenient value to plug into our function. What is a nearby convenient value?
5.
5, okay. So that's our value of a, right?
Mm-hmm.
So we would have to do f of 5 plus f prime of our convenient value times how far are what we're going to call dx, right? How far is our convenient value away from our actual value? So that would be 5, it'd be, I got it backwards. It'd be, oops. You guys tell me, what would it be? Well, it's going to be x minus 5, yeah, right?
Yeah.
And so if we're trying to estimate, there's our linearization. If we're trying to estimate what f of 4.9 is, we would be plugging 4.9 in for x into our linearization, right? Really this is technically, what I did here is not totally right, because this is we're saying that f of x is approximated by this linearization, right? L of x. So now we could use that and say, okay, well, f of 4.9 is going to be approximated by L of 4.9. F of 5 plus f prime of 5 times 4.9 minus 5. Well, we know that stuff. What is f of 5? 3. Plus f prime of 5 is 6 times 4.9 minus 5 is what? Negative 0.1. Now that negative 0.1, doesn't that make sense as a dx? Because that's how far we've pushed the point away from the convenient value. Does that make sense?
Yeah.
Okay. Our convenient value is 5 and we're at 4.9, so we're at our convenient value budged to the left by 0.1. Okay. So what's that give us?
Which is 2.4.
How about that?
Oh my God.
Okay, so here's your party trick. Here's your nerdy
Okay.
college party trick you're going to be able to do. Okay, you can double dog dare your friends to do this, and you'll be able to get the better of them this way. Make them feel kind of silly. So square root of 153, could you estimate that to 3 decimal places pretty accurately? Well, we could, right?
Yeah.
We could, because although 153 is a very inconvenient square root, what would be a nearby convenient square root?
169.
Okay, you could. Is there a closer one?
144.
144. Aha. Okay.
Yeah.
Okay. So then we could say, our function here is, the implied function is the square root of x, right? We've got some function that we're working with. F of x is the square root of x, which is the same as x to the 1/2. That's an easy derivative for us to do. What's the derivative of square root of x?
1/2 x to the negative 1/2.
Okay, so yeah, 1/2 times the square root of x, right? 1/2 x to the minus 1/2, okay? So we could do this pretty easily then. We could say the square root of 153 is going to be approximated by our linearization evaluated at 153, where our convenient value is going to be 144, right? Okay, so we're going to use 144 as our convenient value. Well, this is going to be approximated by the square root of 144, because that's our convenient value. That's A, right? The square root of 144 plus f prime of 144, which is just 1/2 times the square root of 144, easy to calculate, times dx. Well, how far away were we from 144? 153 is 9 away. And where'd that 9 come from? It just came from actually we're -9, right? Right, because
Yeah.
153, to get to our convenient value, we had to go backwards on the graph 9 to the left. And we just get that from 144 minus 153, right? X minus, hold it. Oh, no, never mind. We had it right first time. I confused myself.
Positive.
Right, it's positive 9. Duh. Because 153 is actually to the right of our value of A. Yeah, sorry. So that comes from X, which is 153 minus A, which is 144. Right? And you can do that in your head. You really can. Think about that. Square root of 144 is, but just if you practice it a couple times. What's the square root of 144? 12. So 1/2 times the square root of 144 is just 1/24 times 9. 9/24 simplifies, right?
3/8.
3/8. That's just 0.375. So you got 12.375. Boom. Right? How about that? And you really, I know that sounds like a lot, but try that a few times, practice it 4 times and you'll be able to do it. Not for really complicated functions, but for things that aren't so complicated, like square roots, even cube roots, squared functions, cubed functions. You couldn't do it for like a sine or something like that. That's weird. That's, where you can't really predict the outcomes very well. But you can do it for arithmetic functions like that, where they're just built from powers, And how close are we? Check it out and see. But that's pretty close. What is the square root of 153, somebody? Now, it's going to be off a little bit because 9 is fairly far away from.
12.369316.
Okay, fairly close, right? I mean, that's not bad. Now, what if we had done the square root of 147? Would we have been a lot closer?
Sure.
Way closer, right? Because it's the value of dx. The further we get away from the point of tangency, the more our line is going to deviate from the actual curve, right? So we went away, a fair amount, like going 9 away from 144. That's a fairly big jump, right? Noticeably, the tangent line would start to diverge from the function there. Okay, but it works better for values that are closer to actual square roots. So when you do this in college, you'll really impress your friends more if you pick a value that's closer to a perfect square, right? How about that?
Oh, yeah.
Teaching you guys all kinds of great party tricks.
0.5% off.
Here, let's.
I didn't calculate that right. Don't listen to me.
Okay, so try one. Impress your friends by saying, I bet I could estimate the square root of 48 pretty well.
Do one when she gets back.
Just impress the heck out of her. Yeah, just like I'll throw it out there like you guys, let's just try something. See how close you can get.
Let's see if you guys can just figure this out.
Okay, so try that. Try square root of estimate square root of 48. See if you can do it in your head.
Okay.
Go.
In our heads?
Yeah, it's a square root function. So what's f of x?
Square root of x.
Square root of x.
Okay.
What's f prime of x?
Okay.
Right, 1/2 square root of x, and that's one we do all the time, so you know it. So all you really need to do is you need to figure out what's your a and what's your dx. So for 48, what would a be? 49. And what's your dx going to be? What's the number that's going to go here? How far are you away then?
1.
But you're
Negative
-1, because 48 is 1 to the left, right? So what do you get? Give it to me as a mixed number.
Wait, it would be 7 plus 7 minus 1 over 1/14.
That's it.
Yeah.
Right. So it's going to be 6 and 13 14. Is that what you said?
Yeah,
Yeah,
6
nice.
and 13.
Nice.
That's fantastic. Okay, what's the tip of the day on
Oh, okay, yeah. You guys
We
get it.
gotta
Okay,
start
we'll
with
do
it.
the Big Benford's Law one next
Okay.
week. Yeah.